The next concept, pretty natural, where this comes from, we can define continuity from the left only or from the right only. And so that involves either just a left limit or a right limit. So let me explain. So f of x is continuous from the left at x equals a if that left-sided limit as x approaches a from the left, if that is equal to our function value f of a. And f of x is continuous from the right at x equals a if our right-sided limit is equal to the function value f of a. So we won't see near as many questions with these, but it's definitely, we need to know that that exists. It's also not as important going forward, but you know, sometimes these things pop up and we definitely need to make note of them now. So let's look at one example, and I've got another piecewise function. Whenever you see a piecewise function in the chapter on limits, you know, be thinking, you know, either a left limit or a right limit, really especially around where that transition happens. Okay, so here we have h of x equals x squared when x is less than 1, and then it turns into the natural log of x when x is greater than or equal to 1. All right, so the first question here, is h of x continuous from the left at x equals 1? Okay, so remember our definition of continuity from the left. We're just asking this question: does the left-sided limit, the limit as x approaches 1 from the left of our function, does that equal the function value there, h of 1? If it does, we know it's continuous. Okay, well, let's see. We just need to look at each one separately, and then we'll know. Let's take a look at that limit. And I think might as well just show you all of my work here. You can see the answer, but okay. So taking the left-sided limit, well, we know we're taking the x squared because those are the values a little bit smaller than 1. So we'll just plug 1 right into that, and we'll get that left-sided limit equals 1. But what about the function value? Well, here is where we need to look at where x is allowed to equal 1. So we need to pick the natural log, since that's where it would equal 1. So plugging 1 into the natural log, and if you recall, the natural log of 1 equals 0. That's what calculators are for. If you don't remember that, the natural log of 1 is 0. Well, are these equal? No. The limit, the left-sided limit is 1, but the function value is 0. They don't equal, so no, this is not continuous. Okay. And that's all we need to say. There really are not different types of discontinuities from the left or the right. There's either just continuous or discontinuous, since you're only looking at one side. What's part B? Well, kind of predictable. Is it continuous from the right at x equals 1, right? That transition point. Say, okay, well, we'll go through the same process, but now looking at the right-sided limit. Okay, and it's going to be tough to fit all this on the screen if I'm able to at all. Hopefully you're writing these things. Here's my work, and this one turns out to be okay. The limit, down here, the limit as x approaches 1 from the right. Now we're going to use the natural log, since those are the values a little bit bigger than 1. So we'll plug 1 right on into that and get 0. Okay. Also, the function value, well, we already found this a moment ago, but let's do it again. That's where the function equals 1, so we'll pick the natural log again, plugging 1 into that. Well, it's the same thing we're plugging in. So yes, 0 equals 0. It is continuous from the right. Okay. Moving along. What you're about to see, this is really what it's going to boil down to, and the significance of continuity. Once we have our heads wrapped around what continuity is, and how to check for it. This is what we need, what's coming. There's two theorems that are going to allow us to make progress towards the derivative coming up pretty quickly. So this theorem says these functions are continuous on their entire domain. So we've got these 7 families or types of functions: polynomial functions, rational functions, root functions, so that's square root functions, cube roots, that sort of thing. All the trig functions, all 6 trig functions, the inverse trig functions, all exponential functions, and all logarithmic functions. These are all continuous on their entire domain. And so let me speak to that just for a moment. You might be thinking, hey, wait a second. You know, we had a rational function earlier, an earlier example, and that rational function, it had a hole and it had a vertical asymptote. So how can you come in and say all rational functions are continuous on their entire domain? Also, the trig functions, right? We know tangent has vertical asymptotes. What's up with that? Those aren't continuities, right? That's absolutely true. However, where those holes or asymptotes occur, those are not part of the domain. And so we're careful here. We're saying on the domain it's continuous. And we did see examples later with those piecewise functions where there were discontinuities on domain values, right? Where like a jump happens or something. We even saw that in the previous example a moment ago, right? It was continuous from the right, but not from the left because there was a jump going on. Yet the x value, x equals 1 in question, was a domain value. Okay, so yes, there are vertical asymptotes and there could be holes, but those are not included in the domain. So we can get away with this. But really the idea is, you know, everywhere else, so ignoring the vertical asymptotes and things, right? Especially like polynomials, like they are these nice smooth things. There's no jumps or anything like that happening. Okay, and same for the rest on their domain. So how is this helpful? Well, it's going to lead us, a little gap there, it's going to lead us to this theorem. And this is the key. If f of x is continuous at x equals a, and we already know all those functions, all those 7 types of functions before are continuous on their entire domain. So if you have a function and it's continuous at a certain value, then the limit as x approaches a for a composite function, f of g of x, is equal to f of, and it's like we're pushing the limit past the f. F is continuous. So because f is continuous, we can push that limit through f and do this in the reverse order. We can take the limit of g first and then take that answer and plug it into f. So instead of doing the limit of f of g of x, we can take the limit as x approaches a for g of x. That number gets plugged into f because f is continuous. We can bypass that in our operations. Okay, so let me show you. I know it's like blowing you away. Just kidding. You're like, what's the big deal? Let me show you an example. We're now able to do limits of functions that we were not able to do before. So just one quick example I think will be helpful. Let's take a look at the limit as x approaches 0 for the cosine of 2x squared. Okay. We can move that limit inside. We've never seen a limit like this, right? Involving a trig this way where we've got this composite function. So we've got 2x squared is inside cosine, right? That is a composite right there. Because cosine is a trig function, and because all trig functions are continuous on their domain, we can push that limit inside and do this limit of this polynomial first. So we know this one, we can just plug that 0 in, and well, 2x squared with the 0, 0 squared is 0, and we'll take that result and just put it into the cosine, and hopefully you guys remember the cosine of 0 is equal to 1. So this now opens the door for lots of different combinations of functions and composite functions. So we can combine trig functions with roots, with exponentials, and we can just go totally nuts on the types of functions we can look at. And we know so long as that the one on the outside is continuous everywhere, which cosine definitely is, then we can just plug that 0 right in here. Now the thing is, in practice, you're probably not going to show this middle step. You're probably just going to say, oh, cosine 2x squared. Perfect. I'm just going to plug the 0 right in. And you'd probably skip this step here. You just go straight to this step, cosine of 0, and then, realize that that equals 1. Okay, very, very powerful. That's going to help us out going forward. All right, there's one more part to this section. It's coming up next.